Imagine for a second dropping over 5,800 pounds in today's money on a brand new, highly anticipated computer system.
Right, a huge investment.
Exactly.
Yeah.
So you unpack this futuristic-looking box, you set up the monitor, and you sit back, ready to experience the absolute cutting edge of office technology.
You're expecting a premium experience.
Oh, totally. But then you put your hands on the keyboard, and typing on it feels exactly like pressing down on a set of wooden Scrabble tiles.
Oh man, yeah. It shatters the illusion almost instantly. I mean, you've essentially paid for a sports car, and the steering wheel is made of concrete.
That is the perfect way to put it. And, the nightmare doesn't even stop at the keyboard.
No, it gets worse.
Right. You reach for the mouse to navigate this machine, but you find that using it normally is so frustrating you eventually just give up, flip the entire thing upside down, and start rolling the little tracking ball with your palm.
Like you're playing an arcade game of Missile Command.
Yes. Exactly like Missile Command. Oh, and just as the cherry on top, if you leave your floppy disk in the main drive for too long, it physically overheats. You are quite literally baking your data.
It's a terrifying physical reality for anyone who understands how delicate magnetic storage actually is.
Yeah.
I mean, the sheer anxiety of that user experience is something modern computing has completely insulated us from.
It really has. Well, welcome to the deep dive. Today, we are looking at the ACT Apricot F1.
A truly fascinating machine.
It is. It serves as an absolute masterclass in the chasm between grand technological ambition and the harsh physical realities of hardware in the mid-1980s.
Yeah, the ambition was there, but the execution, well.
Yeah, lacking. So we're using a very specific set of sources for this journey today. We've got an October 1984 Benchtest review from Personal Computer World magazine.
A classic publication.
Oh, definitely. And we've paired that with historical inflation data to adjust those 1984 price tags to our current year of 2026.
Because context is everything with these prices.
Exactly. So our mission today is to examine exactly how ACT tried to build a computer of the future and why their flagship feature, which was a completely wireless infrared keyboard backed by genuinely brilliant software engineering, failed so spectacularly in the real world.
The Apricot F1 is really one of those rare historical artifacts that gets almost everything right conceptually,
Right.
but then it gets almost everything wrong physically. It's just a perfect storm of cost-cutting colliding with visionary design.
It really is. Now, before we even crack open the case to look at the missing chips or, talk about the overheating floppy drives, we really need to address the sheer chaos surrounding the birth of this machine.
Oh, the naming situation.
Yes, because even the name of the computer was a disaster before it hit the shelves. ACT, the company behind it, didn't actually want to call it the Apricot F1.
No, they didn't. I mean, the entire architecture and marketing strategy was originally built around a completely different name.
Right.
They intended to call this machine the Rascal.
The Rascal, which is honestly a bold name for a business computer.
Yeah, it really is.
I mean, it sounds like a mischievous pet, right? Not a serious spreadsheet machine. But they didn't just casually toss this name around in board meetings. They fully committed to it.
Oh, they committed to it at the manufacturing level. The reviewer from Personal Computer World notes that ACT was so confident in the Rascal branding that they actually went ahead and printed the word Rascal directly onto the internal printed circuit boards.
Inside the production machines.
Exactly. Right onto the PCBs.
Wait, so they silk screened the name onto the literal fiberglass of the motherboards?
Yeah, they did.
That's not something you can just wipe off with a bit of solvent. I mean, once you etch and bake a PCB, that text is permanent.
Precisely. You have motherboards rolling off the assembly line, ready to be placed into cases, completely permanently stamped with a brand name they couldn't legally use.
Because someone, somewhere, forgot to check the trademarks.
Yeah. According to the reviewer, somebody at ACT made a very late, very alarming discovery. The trademark for the name Rascal was already registered to someone else.
Of course it was.
And the reviewer Riley notes that it was registered in, quote, Outer Mongolia or some such place.
Outer Mongolia.
Right. Now, whether it was literally Outer Mongolia or just a competitor in another market, the legal obstacle was absolute.
I just can't imagine the panic in that manufacturing plant. You've got thousands of boards stamped with Rascal, and the legal department comes sprinting onto the factory floor, waving a cease and desist.
It must have been chaos.
So they have to pivot at the absolute last second. They abandon Rascal, They lean heavily on their existing successful Apricot brand name and just slap the F1 designation onto it.
Which really highlights the incredible volatility in the Wild West environment of micro-computing companies in the early 1980s.
Yeah.
The reviewer actually notes that micro-companies spent months agonizing over registered trademarks, copyright, and all the other bureaucratic obstacles that stood in the path of getting hardware out the door.
So true.
So the naming debacle of the F1 isn't just a funny footnote, you know? It's a symptom of a marketplace moving so fast that companies were constantly tripping over their own feet.
Which perfectly sets the stage for the compromises they had to make to get this machine to market. We really need to talk about the cost, because to understand the Apricot F1, you have to understand the specific market tier it was trying to dominate.
Right.
The review repeatedly refers to the Apricot F1 as a skinflint machine.
Skinflint.
It calls it an inexpensive small system pitched firmly at the quote-unquote 1,000-pound business machine market.
It was intended to be the budget option, but budget in 1984 means something entirely different than it does today.
Oh, massively different.
Let's break down the original pricing from that Benchtest. The base unit, just the computer itself, no screen, was £995.
Okay.
But obviously you need a display, so if you wanted the official color monitor to go with it, that was an additional £395.
Which brings the total system price to £1,390 in 1984 money.
Correct. Now, to understand the true weight of that cost, we have to apply our 2026 inflation data.
Right, let's do the math.
When we calculate the purchasing power parity, we have to apply a multiplier of roughly 4.17 to those 1984 figures.
Okay, let me do the mental math on that.
Right.
So a multiplier of 4.17 on the 995-pound base unit brings it to roughly 4,150 pounds today.
Right.
And the 395-pound monitor translates to about 1,648 pounds. So to buy this complete, inexpensive, quote-unquote, budget system, a business or an individual is dropping an eye-watering 5,800 pounds in modern money.
It's a staggering figure for a machine defined by its compromises.
Yeah.
I mean, for nearly 6,000 pounds today, you expect absolute, uncompromising peak performance.
You're buying a top-of-the-line workstation for that price, like a really high-end used car.
Exactly. But in 1984, that same relative financial investment bought you a machine that was deliberately stripped down to its bare essentials just to hit a price floor.
It's just wild to think how inaccessible computing was back then. People were stomaching massive financial hits for hardware that was fundamentally crippled out of the box to save pennies on the manufacturing line.
Very true.
And that leads us directly into what was actually going on under the dull cream plastic casing of the Apricot F1. Because if you pull off the lid, which, by the way, the reviewer mentions only takes about 30 seconds and 2 screws, what do you actually find on that motherboard?
Well, you find a very traditional, very conservative approach to engineering. At its core, the F1 is powered by a true 16-bit Intel 8086 processor clocked at 4.77 megahertz.
Okay.
This is paired with 256 kilobytes of RAM and 32K of ROM.
256K of RAM.
Yeah.
And the review makes a specific note about that RAM, doesn't it? It has no parity checking.
Right. So parity checking was a standard method for ensuring memory reliability. Essentially, it uses an extra bit of data for every byte to check if the memory has been corrupted by a random electrical fluctuation or, a cosmic ray.
A stray cosmic ray, yeah.
Leaving out parity checking chips is a classic aggressive cost-saving measure. It saves a few pounds on silicon, but it slightly increases the risk of a silent system crash if a bit just randomly flips in memory.
Wow. They were hunting for every possible corner to cut. And the way they built the rest of the board reflects that too, right? They didn't use any custom logic chips.
The reviewer explicitly points out that contrary to modern trends of that era, there isn't a single custom ULA and uncommitted logic array anywhere on the board.
Okay, to clarify for you listening, a ULA is essentially a blank slate chip that a manufacturer can program and customize to do very specific, efficient tasks just for their hardware. It basically combines the jobs of dozens of smaller chips into one clean, bespoke package.
Exactly. It's elegant, it saves space on the motherboard, and it reduces power consumption. But designing a custom ULA requires upfront capital. It requires R&D.
Right.
So instead of custom silicon, ACT made extensive use of standard 74LS TTL chips. These are just off-the-shelf, generic electronic building blocks.
So it's basically the difference between hiring a master tailor to make a single perfectly fitted suit versus buying 50 generic fabric patches and sewing them together yourself. The patchwork suit still covers you, but it's bulky, it's inefficient, and it's definitely not elegant.
That's a perfect way to put it. But, the real story of the Apricot F1's motherboard isn't about the chips they used. It's about the chips they completely left out. There are very specific, intentional, empty spaces on this board.
The missing brains. Let's start with the first major omission, the 8087 math coprocessor.
Right. So the main processor, the Intel 8086, is a generalist. It's fantastic at moving data around and managing the operating system using integer arithmetic.
Sure.
But it is notoriously slow at floating point mathematics, the really complex decimal calculations required for heavy financial spreadsheets, early CAD software, or 3D rendering.
So if you're a power user, you would normally buy an 8087 math coprocessor and plug it into a dedicated empty socket right next to the main brain on the motherboard. It basically acts as a specialized calculator.
Right. But on the Apricot F1, not only is the 8087 chip missing, which, to be fair, was standard for budget machines to leave the chip out.
Right, you'd buy it later.
Exactly. But the physical plastic socket to plug one into is entirely absent from the board.
They didn't even give you the option to upgrade. Why leave off a plastic socket? That can't cost more than a few pence.
Well, it's not just the cost of the plastic. It's the cost of the board space, the cost of routing the copper traces to connect that socket to the CPU, and the tiny bit of solder and time required on the assembly line.
Unbelievable.
The reviewer notes that ACT apparently felt the demand for heavy mathematical processing in a budget machine just didn't justify that literal manufacturing cost.
That is extreme cost cutting. I mean, if
Yeah.
you bought this 500 to 800-pound machine and a year later your business needed to run complex statistical analysis, you're completely out of luck. You couldn't just open the case and plug in an upgrade.
Nope.
The machine was fundamentally capped by the manufacturer's refusal to solder a piece of plastic.
But as glaring as the missing AZU87 is, it's the second omission that truly crippled the machine's architecture.
Oh boy.
The missing DMA controller.
Okay, I know leaving this out was a massive bottleneck, but break down exactly what a DMA controller does and why the F1 suffered so badly without it.
DMA stands for direct memory access. To understand why it's crucial, you have to think about how data moves inside a computer. When you load a program or open a file from the physical floppy disk, that data has to travel from the incredibly slow mechanical disk drive into the incredibly fast electronic system memory, the RAM.
Right.
Normally, a DMA chip handles this entire transaction. It is a dedicated traffic controller whose only job is to manage the flow of data between the disk drive and the memory. It establishes a direct pipeline. This is vital because it frees up the main CPU to keep doing other computational tasks.
Okay, think of the motherboard like a high-end restaurant kitchen. The main CPU is your head chef, managing all the complex cooking. The disk drive is your pantry all the way in the back, and the RAM is your prep station right in front of the chef. A DMA chip is like having a dedicated sous chef.
I like this analogy.
So when the head chef needs a 50-pound bag of flour from the pantry, he yells to the sous chef, "Bring me the flour!" The sous chef goes to the pantry, lugs the flour to the prep station, and while that's happening, the head chef never stops cooking the intricate sauces on the stove.
That's a phenomenal analogy because the CPU operates on clock cycles, millions of them a second.
Right.
If it has to manage the data transfer itself, it wastes those cycles.
Right.
So what happens in the Apricot F1's kitchen where there is no DMA sous chef?
Well, every single time you need an ingredient from the pantry, like every time a kilobyte of data needs to load from the disk drive, the head chef has to put down his tongs, turn off the stove, walk all the way into the back pantry, find the flour, physically carry it to the prep station, and only then can he resume cooking. The entire kitchen grinds to a halt, while the smartest brain in the room does basic manual labor.
Exactly. In computer terms, this is called programmed I/O. Every single byte of data that moves off the disk has to be personally read by the main 8086 processor and then written into the RAM by the main 8086 processor.
It's so inefficient.
It is incredibly inefficient. Now, the reviewer points out that if you were just running standard MS-DOS, this wasn't a catastrophic problem. MS-DOS was a single-tasking operating system.
So the chef was only ever cooking one meal at a time anyway. If he has to go to the pantry, the single meal just takes a little longer.
Right. But ACT heavily promoted the fact that the Apricot F1 also supported concurrent CPM. This was an advanced operating system designed to handle multiple tasks at once through time slicing. You could have a word processor open while a database compiled in the background.
Oh no, I see where this is going.
The reviewer explicitly notes that if you tried to run concurrent CPM and you had two different background jobs trying to access the disk at the same time, this lack of DMA caused major systemic problems.
I bet.
The CPU just couldn't juggle the active processing of multiple programs while constantly being interrupted to run back and forth to the disk drive to manage the data flow. The collisions caused the system to bottleneck severely.
So to hit that specific price point,
Yeah.
they fired the sous chef, forced the main brain to do all the grunt work, and consequently made multitasking an absolute nightmare. Which means that 8086 CPU is working incredibly hard, constantly fetching its own data, and when electronics work hard, they generate heat.
Which brings us perfectly to the physical design of the main unit and how ACT decided to deal with all that thermal energy.
Let's look at the box itself. Because with a CPU working that hard, you'd expect a robust cooling system. But the physical design of this machine completely ignored the basic laws of thermodynamics.
The design of the F1 is really a study in dense, heavy contradictions. On one hand, it was marketed as a compact, sleek desktop unit. It used a traditional 3-box setup main system unit, separate keyboard, separate display, but the main unit itself was remarkably small.
Yeah.
The reviewer notes it managed to accommodate the entire system in about a third of the space taken by most other computers of the era.
It's described as a dull cream box that is very narrow, but quite deep. The top is a two-stage affair. The back half is taller to accommodate the bulky internal power supply, but the front half is entirely flat. And it's flat for a very specific, terrifying reason.
It serves as the pedestal for the monitor. And we have to remember, we aren't talking about modern, lightweight, flat-screen LCDs. In 1984, computer monitors were massive, incredibly heavy glass cathode ray tubes.
The review mentions the system could be bundled with a Sony Trinitron color monitor, or, hilariously, a massive microVitek monitor that the reviewer notes was temporarily housed in a couple grand's worth of pre-production, hand-carved plastic casing.
That's wild.
I just love that image.
Right.
This tiny, sleek, narrow, dull cream box with a gigantic, hand-carved plastic CRT crushing down on top of it, just looming over the desk.
The physical weight of those CRTs was immense, and to prevent the monitor from literally crushing the computer casing, ACT had to use a massive amount of internal shielding.
Okay.
The reviewer notes that once you take the top off, the first thing that strikes you is that there is heavy metal shielding everywhere. There's a massive shield over the front of the unit, and even the disk drive has heavier than usual metal shielding around it.
This dense metal cage serves two purposes, right?
It does. First, it acts as a Faraday cage. A massive CRT monitor sitting directly on top of delicate computer circuitry generates a massive magnetic field and a lot of electromagnetic interference. The shielding prevents that interference from scrambling the data on the motherboard.
Makes sense.
But its second, and perhaps more vital task, is structural integrity. It physically reinforces the plastic lids that the heavy color monitor can be safely rested on top without bowing the plastic or snapping the logic board underneath.
So let's paint the complete picture here. You have a very small, dense, heavily shielded, narrow metal box. Inside that box, you have a CPU that is running hot because it doesn't have a DMA chip to help it move data, so it's working overtime.
Yep.
And sitting directly on top of this tiny box, acting like a lid on a pot, is a massive heat-generating CRT monitor. How on earth are they flushing the heat out of this system?
That is the most alarming engineering decision of the entire machine. They aren't using a cooling fan.
I'm sorry, no fan at all. In a dense metal box with a CRT on top.
No fan whatsoever. All cooling for the system is achieved entirely by convection.
Okay, explain how convection cooling is supposed to work here and why it's so incredibly risky for this specific setup.
Convection relies on the natural principle that hot air rises. The theory is that as the internal electronic components heat up, they heat the air immediately surrounding them. That hot air naturally rises and escapes through vents cut into the top of the casing.
Okay.
As the hot air leaves, it creates a slight negative pressure, which draws cooler ambient air in through vents at the bottom of the case. It creates a natural chimney effect. It's entirely passive. It relies entirely on the ambient temperature of the room being cool and the uninterrupted flow of air.
But the top of the case is covered by a massive CRT monitor. And even if it wasn't, this is an office machine. What happens when someone carelessly drops a training manual or a stack of papers on top of those vents?
The chimney effect stops immediately. The heat has nowhere to go. It just bakes inside the heavy metal shielding.
And what is sitting right in the middle of all this trapped rising heat?
Yeah.
The floppy disk drive.
Exactly. The F1 uses a 720K double-sided Sony 3.5-inch microfloppy drive. Now, mechanically, this was a fantastic piece of hardware for 1984. Most computers were still using large, floppy 5.25-inch disks. These new 3.5-inch microfloppies were enclosed in hard plastic with a sliding metal shutter. The reviewer notes the drive itself performed faultlessly, was very fast, and could happily read older single-sided disks.
But its physical location, inside a passive convection-cooled oven, created a major psychological nightmare for the user.
It really did. The reviewer explicitly states that their only major reservation about the disk drive is that it tends to overheat dramatically. They write, and I quote, "If you left a disk in the drive for any length of time, it would be hot to the touch."
Hot to the touch. That's not a phrase you want associated with your data storage. Let's think about the physics of a floppy disk. You are storing your vital data magnetically on a very thin, flexible piece of mylar plastic coated in iron oxide.
Heat is the natural, devastating enemy of both thin mylar plastic and magnetic alignment.
Wait.
If you heat up a magnetic surface enough, the kinetic energy causes the magnetic domains to scramble. It loses its data.
It's terrifying. Let me ask you, listening directly, would you trust your life's work, your corporate financial spreadsheets, or your novel, to a floppy disk that you had to pull out of the drive and literally let it cool down on the desk before you could safely put it back in its paper sleeve?
Now, to be fair to ACT, the reviewer does note that while it was highly disconcerting, they didn't actually experience any hard reliability problems or data corruption during the bench test. The drive kept working.
But from a user experience standpoint, it's a complete disaster. It creates massive, constant anxiety. Every single time you press the eject button and you pull out a metal shutter that feels like it just came out of a toaster, you are physically reminded that your data is baking inside a metal box.
It's the ultimate friction between the physical world and the digital world. The software might be working perfectly, but if the physical object feels dangerously hot, human instinct takes over. You fundamentally stop trusting the machine.
Absolutely. And speaking of the friction of the physical world, we have to step back from the hot, dense main unit and look at the Apricot F1's most famous, most ambitious, and ultimately most fatal flaw. Because as bad as the convection cooling was, the way the user actually interacted with the machine from across the desk is what cemented its legacy.
We are talking, of course, about the flagship gimmick, the completely wireless keyboard.
In 1984, the idea of a wireless keyboard was basically science fiction. People were used to thick, coiled cables tying their peripherals to the heavy box.
It really was a futuristic pitch. The reviewer notes that normally the keyboard is not one of the most interesting aspects of a microcomputer, but that is certainly not the case with the F1.
Not at all.
The most striking feature of the keyboard is that it doesn't use a physical cable. ACT chose to use an infrared light beam to transmit keystrokes across the desk.
Now, they weren't the first company to try this, but they were actively trying to fix a recent massive failure in the industry. Right?
Yeah. Yes. The reviewer points out this is only the second time they'd ever seen this idea implemented on a microcomputer. The first machine to try an infrared keyboard was the IBM PC Junior. And on the PC Junior, the light beam was, quote, a disaster.
Why was the IBM version such a catastrophic failure?
Because infrared communication relies on sending pulses of light, and offices are full of light. Ambient sunlight through a window, desk lamp, or the high-frequency flickering of fluorescent office tubes can easily interrupt, scatter, or misread a simple light pulse. On the IBM PC Junior, the signal constantly got garbled on its way to the main unit.
What happens when a signal gets garbled? Does it just drop the letter?
That's the best-case scenario. At best, the machine just didn't understand what you typed, and a letter went missing.
Okay. And at worst?
At worst, a garbled light signal would accidentally translate into a completely different valid command string. The computer would execute it, creating absolute havoc. You could be typing an A, a fluorescent light flickers, the receiver gets confused, and the computer decides you just hit delete page.
Oh man, that is completely unusable. So ACT looked at the IBM PC Junior disaster, and instead of saying infrared is a bad idea, their engineers said, we can fix the physics of light with the mathematics of software. And to their immense credit, the software solution they built was a genuine marvel of engineering.
It truly was. To solve the IBM problem, ACT developed their own proprietary error detection and correction system using what's called a Hamming code.
Okay, we need to dive deep into this.
Yeah.
What exactly is a Hamming code, and how do they adapt it for a computer keyboard in 1984?
A Hamming code is a mathematical algorithm originally developed by Richard Hamming at Bell Labs in the 1950s. It's heavily used in telecommunications to detect and correct errors in data as it's being transmitted over noisy channels, like an infrared beam cutting through a brightly lit office. On the Apricot F1, every single time you pressed a single letter on the keyboard didn't just send a simple short ping of light, it blasted out a complex 32-bit packet of data.
32 bits of data just to say I pressed the letter J.
Yes. And the way those 32 bits were divided is the genius part. Only 8 of those bits were actually used to identify the payload, the actual ASCII character you pressed.
Okay, so 8 bits for the letter J. What were the other 24 bits doing?
The reviewer notes that an incredible 12 bits were dedicated purely to error detection and correction.
Wait, hold on. 12 bits for error correction and only 8 bits for the actual letter. That's a massive amount of computational overhead. They are dedicating 50% more data to ensuring the letter arrives safely than to the letter itself.
It's a huge ratio, and it shows how terrified they were of the IBM PC Junior's reputation. It works by adding redundant parity bits. Before the keyboard sends the light pulse, its internal processor calculates a complex mathematical signature based on the 8 bits of the letter you pressed. It weaves that signature into those 12 correction bits and sends the whole 32-bit package across the desk.
So when the light beam hits a receiver on the computer has to do the math in reverse in real time.
Exactly. The receiver captures the light, looks at the 8 bits of the letter it received, calculates what the mathematical signature should be, and then checks it against the 12 correction bits it actually received. If the signatures match perfectly, the computer knows the letter arrived without interference and prints it on the screen.
And what if a desk lamp glared, or someone walked past, and a piece of the light signal got corrupted?
This is where the Hamming code is magical. If the signatures don't match, the algorithm calculates what's called the Hamming distance. The code is sophisticated enough that the computer can often figure out exactly which specific bit got flipped by the desk lamp.
Wow.
It flips it back, corrects the error entirely on the fly, and prints the correct letter on the screen, all without the user ever knowing the signal was compromised.
That is an incredible feat of processing for a budget machine in 1984.
And the most impressive part is that it actually worked. The reviewer was amazed by this supreme effort. They actively tried to fool the system to see if it would fail like the IBM did. They pointed the keyboard away and bounced the infrared signal off the walls of the room. They took the keyboard way beyond its rated 2-meter range.
And did it work?
The Hamming code held up flawlessly. Invariably, it either registered the correct key, or if the signal was entirely blocked, it simply didn't register at all. It never, ever wrongly interpreted a key.
So, you have a triumph of mathematical engineering, a flawless software protocol. And yet, if you ask any computer historian about the Apricot F1's wireless keyboard, they will tell you it was a complete failure. Why? Because while the software was perfect, the physical hardware was a nightmare.
It is the tragic irony of the Apricot F1. The software ambition was entirely kneecapped by physical limitations and cheap manufacturing. Let's start with the build quality. The reviewer notes that the keyboard signal is fairly directional. When the review machine first arrived, the keyboard would only work if it was placed perfectly dead center in front of the main unit.
Which entirely defeats the purpose of a wireless keyboard. You want to be able to lean back, put your feet up, and type from your lap.
Exactly. And when the reviewer physically looked closely at the keyboard casing to see why the signal was so weak, they found the problem. The infrared LED transmitters, the little glass bulbs inside the keyboard that actually shoot the light, were physically badly aligned from the factory.
What do you mean?
They were pointing internally at the plastic casing, not out the window.
Quality control just completely failed. So what did the reviewer have to do to make this cutting-edge wireless technology work?
They had to take a screwdriver, open up the keyboard casing, reach in, and literally bend the metal legs of the LED bulbs back into shape with their bare fingers so they pointed out the front.
You're kidding.
Nope. Once they physically bent the hardware, the signal improved and it became usable at different angles.
Expecting a business user who just paid nearly 6,000 inflation-adjusted pounds to crack open their brand new keyboard and bend the internal components is absurd. But even after you bend the LEDs, you still have to deal with the stubborn physics of light.
Right. The reviewer points out that the path from the keyboard to the main unit has to be relatively free from obstructions. It doesn't mind a stray piece of paper, but it objects strongly to a very common, very human use case.
The desk lip.
Yes. The whole point of cutting the cord is that you can put the keyboard on your lap, lean back in your chair, and type. But the reviewer found that if you put the F1 keyboard on your lap, the physical lip of the wooden desk often blocked the direct line of sight between the keyboard in your lap and the receiver sitting on top of the desk.
Ah, right.
The infrared beam simply couldn't punch through solid wood. The geometry of a standard sitting posture defeated the technology.
The human body and a piece of wood outsmarted a 32-bit Hamming code. But the absolute funniest physical failure of this system, the flaw that makes it truly legendary, is the office crosstalk.
Oh, the crosstalk is the ultimate oversight in product design.
Okay, picture an office in 1984. The boss decides to modernize the accounting department, so they buy 4 Apricot F1s and set them up on 4 desks in the same room. What happens when the accountants start typing?
Absolute chaos. The reviewer points out a major fundamental flaw in how ACT deployed the wireless system. The keyboards are not keyed or paired to individual system units. They all use the exact same light frequency and the exact same Hamming code structure. There is no unique identifier for desk A versus desk B.
So if you line up 4 F1s in an open-plan room, and you pick up one keyboard and hit a key,
all of the computer receivers in the room see the light pulse, decode it perfectly using their Hamming code, and register the keystroke. You type the letter Q on your desk, and Q appears on your screen, your coworker's screen, and the boss's screen across the room simultaneously.
it's not a dedicated peripheral, it's a localized broadcast system. You are essentially shouting your keystrokes to the entire room.
It makes deploying these machines in a standard business environment completely impossible. You couldn't have 2 in the same room without them constantly interfering with each other's work.
Wait, ACT realized this was a problem before they shipped, right? They provided a solution in the box for the office crosstalk. And this solution is perhaps the single most depressing compromise in the entire review. What did they supply to fix their cutting-edge wireless interference?
To solve the problem of their wireless keyboards talking to every machine in the room, ACT supplied a length of physical fiber optic cable in the box.
A cable.
You could use this cable to literally plug the keyboard into the front of the system unit.
Wait, hold on. They built a 32-bit error-correcting wireless protocol. They fought the physics of light, and their ultimate fix was to put a literal leash on it.
Yes, the fiber optic cable contained the light signal within a physical tube, preventing it from broadcasting across the room and stopping the interference.
That completely defeats the purpose of the wireless keyboard. You end up with a wired keyboard anyway, just a vastly over-engineered light-based wired keyboard that you can't even use on your lap because the fiber optic cable is rigid and delicate.
It is the ultimate concession to physical reality. They built a 1990s conceptual interface using 1980s hardware limitations, and they had to fall back on a piece of string to make it actually work in a real-world office environment.
It's tragic and hilarious at the same time, but even if you fixed the infrared beam with the fiber optic cable, the physical act of typing on this thing was an ergonomic disaster. Let's talk about how the keyboard actually felt under the hands.
We've talked about how the signal gets to the computer, but how does it actually feel to generate that signal? The answer is terrible. In an effort to make the keyboard unit ultra-low profile, sleek, and compact, ACT made a very controversial design choice. For the first time on one of their machines, they moved away from a traditional mechanical switch keyboard and used a membrane layout.
Explain the difference between a mechanical switch and a membrane, and why it matters so much to a typist.
A traditional mechanical keyboard has a separate, physical, spring-loaded switch underneath every single keycap. When you press it, you feel a distinct tactile bump, and you hear a click when the electrical contact is made. It provides instant physical feedback to your fingers that the key registered. A membrane keyboard replaces all those individual switches with a flat, pressure-sensitive plastic sheet with printed circuits on it. The keycap just squishes a rubber dome down onto the flat membrane to close the circuit.
From a manufacturing standpoint, membrane keyboards have massive advantages,
Yeah.
right? Especially for a machine trying to hit a budget price point.
Absolutely. They are vastly cheaper to produce because you're printing a sheet rather than assembling dozens of individual switches. They are much thinner, allowing for a lower profile casing. And, theoretically, because there are fewer moving hard parts, they are supposed to be more resilient to dust or spills.
But the trade-off is almost entirely in the tactile feel. You are sacrificing the user experience to save money. The reviewer is absolutely scathing about this membrane implementation. They write, "I have yet to find one that feels anywhere near as good as a traditional unit."
The reviewer provides a very visceral description of what typing on the F1 actually feels like. They explicitly say the keys look, feel, and sound exactly like the pieces in a Scrabble set.
Scrabble tiles. Imagine being a professional secretary or an accountant trying to touch-type a 10-page financial report on a flat board of unyielding wooden Scrabble tiles.
The analogy implies a hard, flat, dead surface. There is no travel, no satisfying click, and worse, they didn't actuate easily. The reviewer notes that these Scrabble keys don't register until they've been pressed down quite forcefully.
You can't lightly glide over the keys. You have to aggressively push every single key to guarantee the rubber dome makes solid contact with the membrane below.
It's physically exhausting. Touch typing relies on rhythm and light feedback. The F1 keyboard demands brute force, which slows down your typing speed and causes finger fatigue.
And just when you think the keyboard can't get any worse, there is a specific, fatal geometric design flaw regarding the most important, most frequently used key on the entire board, the spacebar.
Oh, the spacebar is a prime example of aesthetic form completely ruining ergonomic function. The keyboard casing was designed to be ultra-low profile and sleek. To achieve this, they placed the spacebar very close to the bottom edge of the main plastic casing. But crucially, the keycap of the spacebar itself rested significantly lower than the hard plastic lip of that outer casing.
Okay, visualize kinematics of typing. Your fingers are curved over the home row, and your thumbs are hovering low over the bottom. You go to hit the spacebar with the side of your thumb, which is the natural downward sweeping motion. What happens?
When you strike downward with your thumb, the side of your thumb catches on the hard, raised, plastic-edged casing before it can fully depress the spacebar beneath it. The rigid lip of the plastic physically stops your thumb from completing the keystroke.
So how do you actually put a space between words?
The reviewer explains that to make contact, you have to make a conscious, highly unnatural effort to pivot your thumb completely downward, almost pointing it straight down vertically at the desk, just to bypass the casing lip and push the space bar deep enough into the trench to register on the membrane.
You have to change the entire anatomical geometry of your hand just to hit space. That's not just annoying, that's an ergonomic nightmare. Every single word you type requires a conscious, frustrating physical adjustment of your hand posture.
Now, the reviewer does try to be fair here. They note they were using a handmade pre-production keyboard for the Benchtest, but they openly state they couldn't see how the final mass production units would be sufficiently different to make the problem go away. And the fundamental physical layout, the trench the spacebar sat in, was inherently flawed.
So to recap the typing experience, you have a keyboard that you had to pound on like Scrabble tiles. It requires a bizarre, joint-aching thumb dance to hit the spacebar. And if you don't plug it in with a piece of fiber optic string, your private document might show up on your boss's screen across the room.
It's an overwhelming amount of friction just to enter text.
But we can't talk about ergonomics without talking about the mouse, because ACT didn't just bundle a standard mouse with the F1, they bundled a device so uniquely terrible that the reviewer literally suggested it needed to be renamed.
Yes. Also supplied with the review machine was ACT's proprietary version of the mouse. But the reviewer notes that a much more apt name for this peripheral would probably be the Rat.
The Rat. Why?
Because of its sheer comical size. The reviewer states it's about 3 times larger than most other mice on the market at the time. Mice were still a relatively new concept in 1984, but Apple and others were establishing a standard size that fit in the palm. The ACT mouse was a massive, hulking wedge of plastic. It consisted of a large tracking ball underneath and 2 buttons running down each side to enable you to select options.
Okay, so it's a giant heavy brick, but it shares the same technological gimmick as the keyboard, right?
Yeah.
It's wireless.
It is. Like the keyboard, the mouse communicates with the main unit via an infrared light link. And it uses a similar battery-powered LED setup to shoot pulses of light at the main computer box.
Which means it relies on direct line of sight to the receiver on the front of the computer. And this created a massive instinctual usability issue for the reviewer.
It did, and it's a fascinating look at early human-computer interaction psychology. When you hold a pointing device, your brain instinctively wants to point it at the thing you are trying to manipulate. The user is looking at the screen, trying to move a cursor on the screen. So instinctually, the reviewer kept finding themselves pointing the nose of this giant infrared mouse directly upward at the cursor on the monitor.
But the receiver isn't on the monitor.
No, the transparent plastic cover for the infrared receiver is down on the flat front of the main cream-colored unit sitting on the desk. So if you point the mouse up at the screen where you're looking, the infrared beam shoots over the top of the receiver and the mouse instantly stops working. The cursor freezes. You had to constantly fight your own instincts and remind yourself to aim your hand down at the box on the desk while craning your neck up to look at the screen.
It's a total disconnect between physical action and visual feedback. It breaks the illusion of control. And frankly, dragging a giant heavy block of plastic around a desk while consciously keeping its nose pointed at a specific box sounds exhausting.
It was exhausting, but the reviewer found a truly hilarious, highly practical workaround. In addition to being designed to slide around the desk like a standard mouse, the ACT Rat was designed so it could theoretically be used as a tracker ball.
Okay, how did that work in practice?
The reviewer found pushing the giant mouse around the table and aiming it so frustrating that they just picked the entire device up and flipped it upside down. They let it rest on its back on the desk, pointing the infrared LED directly at the computer box so it never lost signal, which exposed the large, heavy tracking ball to the air.
So now it looks like a dead bug with a ball in its stomach.
Exactly. And instead of moving the plastic mounts, the reviewer just ran their hand over the exposed ball, rotating it rapidly in the direction they wanted the cursor to go. They explicitly compare the experience to playing the arcade game Missile Command.
Oh, that's perfect. For those who haven't played it in an amusement arcade, Missile Command used a large, heavy trackball mounted in a console that you slapped and spun rapidly with your palm to target incoming missiles on a screen.
That's exactly how the reviewer ended up navigating spreadsheets on this 5,800-pound business machine.
It is such a brilliant, absurd image. ACT sold you a futuristic, sleek, wireless desktop experience. But the reality of using it was bending LED bulbs with your bare fingers, bruising your thumbs on an unresponsive Scrabble board, pointing a giant plastic rat at the wrong box, and eventually just giving up, flipping the rat upside down, and furiously playing arcade games just to click an icon on a menu.
It is the absolute peak of 1980s hardware compromises. We have a visionary idea executed with the cheapest possible physical components, resulting in a user experience that borders on slapstick comedy.
Which brings us to a really important question. Why was ACT pushing so hard for a mouse and an infrared keyboard in the first place? What were they desperately trying to achieve on the screen to justify this bizarre, frustrating physical setup? Because MS-DOS doesn't need a mouse.
They were trying to build a graphical user interface, a GUI. They wanted an operating system that felt modern, approachable, and visual, long before the underlying hardware architecture was truly powerful enough to support it seamlessly. On the software side, the F1 replaced the old, text-based Apricot Manager program with a brand new successor known as Activity.
And Activity, spelled ACT-ivity, of course, a little corporate branding pun, was heavily reliant on visuals to hide the complexity of the computer.
It was. It sat like a heavy layer on top of the raw operating system and made extensive use of what the manual spelled as icons with a K and that giant ACT mouse. It was an aggressive attempt to be as friendly as possible to the novice end user. It was trying to hide the intimidating, blinking cursor terrors of the raw DOS command line behind friendly pictures of pointing hands, computer disks, and question marks.
They were essentially chasing the Apple Macintosh dream, but on a tight budget. And the review notes some genuinely impressive visual tricks they pulled off to make it feel premium, right?
Yes. When you switch on the F1, you notice the text on the screen behaves differently than a standard DOS PC. It doesn't just jump clunkily from line to line. It features smooth scrolling.
Smooth scrolling. Explain the mechanical difference there.
On a standard, cheap text display, the screen is broken into a grid of character cells. When the text needs to move up a line, the computer just instantly redraws the entire screen, shifting everything one block higher. It's jarring and flickery. Smooth scrolling means the text appears to slide fluidly and continuously up the screen, pixel by pixel, sliding smoothly under the line above it. It's a beautiful aesthetic touch, but drawing graphics pixel by pixel rather than character by character requires a massive amount of processing power and, crucially, a lot of memory management.
And that memory management is where this grand graphical ambition hits the brick wall of that 256K RAM limit we talked about earlier.
Right. By modern standards, 256 kilobytes of memory is microscopic, but even in 1984, it was cramped if you wanted to do graphics. And the F1's graphical ambitions ate up a massive chunk of that RAM before you even loaded a single useful program.
How much overhead are we talking about?
The operating system routines required to run the activity interface, plus the bit mapping required for the graphics display, chewed up just under 90K of the user RAM immediately upon boot.
So out of 256K, nearly 90K is instantly gone just to keep the lights on and draw the icons. That's over a third of your memory.
And 40K of that was taken up purely by the bit mapping for the display. Bit mapping means the computer has to hold the state of every single individual pixel on the screen in its memory, rather than just holding a simple text code. It's beautiful, but it's resource intensive. It left the user with a very cramped workspace for actual applications.
Despite that cramped memory, they bundled a ton of software to try and make it an attractive, complete package out of the box, right? They wanted you to feel like you got your money's worth.
They did. It came with the GSX graphics operating system, which was an attempt to provide a consistent standard interface for writing graphics software across different types of machines. From ACT themselves, you got an interactive tutorial, a program called ACT Sketch, and a database called ACT Diary. And from a company called Sourcem, it included productivity software, SuperPlanner, SuperCalc for spreadsheets, and SuperWriter for word processing.
ACT Sketch was basically their version of McPaint, right? An attempt to show off the mouse.
Essentially, yes. It allowed you to draw basic pictures with arc and line drawing facilities and color filling. It was a toy to get you used to the mouse. And the ACT Diary was a more serious database application used to create an electronic desk diary and manage contacts.
But the diary had a pretty funny visual flaw that highlights how rushed some of this software was, didn't it?
It did. The reviewer notes that at the time of writing the Benchtest, the ACT programmers were apparently still arguing internally over what colors the different screens in the program should be. Consequently, the review version of the diary shipped with a not-so-endearing habit of printing some critical sections as blue text on a blue background.
Blue text on a blue background. The classic blue-on-blue syndrome, which, as a reviewer vastly understates, made it hard to use. It's just another perfect example of the software ambition outstripping the execution, or hardware palette limitations forcing bizarre visual compromises. So looking at this entire package, the naming chaos of the Rascal, the missing DMA chip forcing the CPU to act as a sous chef, the hot floppy drive baking disks, the incredible Hamming code ruined by unaligned LEDs, the thumb-bruising Scrabble keys, and a massive upside-down mouse navigating a blue-on-blue GUI. How did this machine actually fare in the fierce market battle of 1984?
It's very easy to look back with modern eyes and mock it relentlessly, but we have to remember the context of its competitors at the time. The reviewer positions the F1 against its main rivals in that 1,000-pound base unit budget business machine sector. Machines like the Sanyo MCP 5585, the Prism Ren, and the Apple SIGs.
With all those ergonomic flaws, how does it possibly stack up against those?
Surprisingly well, according to the final verdict in the review. Despite absolutely despising the keyboard and the mouse, the reviewer concludes that the F1 actually scores over the Sanyo in a number of important areas. And the absolute most important area that saved the F1's reputation was, ironically, its disk drive.
Wait, the same disk drive that gets hot enough to bake your Mylar data?
Yes. Because despite the terrifying heat, that 720K double-sided Sony microfloppy drive offered a massive amount of storage capacity for the price point. Most competitors were still offering 160K or 360K drives. That single high-capacity component provided enough raw utility and convenience to offset a lot of the interface complaints for a budget-conscious business user.
And ACT wasn't just aiming at businesses. They saw an opportunity to get this compromised machine into schools, too.
Yes, there was a specific educational variant called the F1E. ACT made a concerted, aggressive bid for a slice of the educational market. The F1E was priced and marketed specifically to attack the absolute dominance of the BBC Micro in UK schools.
The BBC Micro was the gold standard for British education in the 80s. How do they try to compete?
The argument ACT made was pure economics. They pitched that for the price of buying a heavily expanded BBC Micro with external disk drives added on, a school could instead buy an F1E, which already had the disk drive built in, and which could theoretically be expanded later into a full-function business micro for teaching serious vocational skills. It was a compelling pitch, even if the hardware had quirks.
It's a fascinating strategy. Sell the future, deliver a compromised present, and hope the sheer utility of the storage space makes people forgive the Scrabble keys. So, to synthesize all of this, if we take a step back and connect the missing chips, the convection ovens, and the infrared failures to the bigger picture, what does the Apricot F1 ultimately represent in the grand history of computing?
It represents a fascinating, beautifully ambitious dead end. The Apricot F1 was a machine desperately trying to deliver a 1990s user experience, a graphical interface, smooth scrolling, wireless peripherals, but it was forced by economic reality to do so using 1984 budget hardware components. The software engineering, like the mathematical brilliance of the Hamming code, was genuinely revolutionary, but it was entirely ruined by the physical friction of cheap membrane keys, misaligned LED bulbs, and missing processing chips.
It's the classic tragedy of being a visionary ahead of your time, but constrained by the budget of your present. Which brings us to the end of our journey today. We've gone from the trademark panic of the Rascal, laughed at the missing sous chef DMA chips bottlenecking the kitchen, worried about our spreadsheets melting in hot floppy drives, and marveled at the fatal combination of flawless, error-correcting code tied to terrible, thumb-bruising Scrabble tile ergonomics and an upside-down mouse.
And as we sign off today, I want to leave you with a final thought to mull over. We look back at the Apricot F1 and we laugh at the absurdity of supplying a fiber optic cable to fix a wireless keyboard. We recognize with the benefit of hindsight that its grand software ambitions required a level of hardware maturity that simply didn't exist yet in 1984. But looking around at our world today in 2026, we have to ask ourselves a difficult question. What modern technologies are we trying to force into our lives right now where the grand software vision is currently being ruined by the physical friction of immature hardware?
Our early VR headsets, where the graphics are incredible but the headset gives you a neck ache after 20 minutes. Our version of the giant rat mouse. Are these new AI hardware pins, where the AI is brilliant but the microphone can't hear you in a crowded room? Our version of the Scrabble keyboard.
Exactly. We are always pushing against the edge of what hardware can comfortably do. What is our generation's 5,800-pound machine with a space bar we can't properly reach?
It's a great question to take with you, and a reminder that the friction between software dreams and hardware reality never really goes away. Thank you so much for joining us on this deep dive. We'll see you next time. And until then, keep your floppy disks cool and watch out for the lip of your desk.